the same thing for the friends, it would be very problematic because they are in isolated labs and this would break the isolation. So now why is this a problem, this thing? I can now analyze the experiment from W's perspective and just calculate what is the probability of the different outcomes. And what we will find, and I will not show this calculation for time reasons, but it's very easy to do, is the following. We will find that the probability at the end that W bar is okay and W is okay is actually 1 is positive. It's even concrete, it's 1 over 12, but that doesn't matter. So in other words, if we repeat the experiment, if we repeat the whole experiment sufficiently often, there will be a round in which this happens. So there will be a round in which W bar is okay. So the announcement is W bar was okay, but then also W is okay. This will happen. But this, of course, is now in contradiction. So here W bar made this statement, whenever he sees W is okay, then he's certain that the W that he will observe later is failed. But it will actually happen that he will observe okay. So the prediction that he made in quantum mechanics, so W just made a prediction using only quantum mechanics and this assumption C, and this prediction turns out to be wrong. He would just observe a value which directly contradicts his prediction, although it was a certain prediction. It was not something like with some probability this will happen. He was certain the outcome will be failed, but he will observe okay. So now, strictly speaking, there is a third assumption to say that this is a contradiction, because a many worlds person would say, oh, that's fine. There is just one copy of the person who sees okay and one who sees fail, and he just made the prediction for one copy and was then in the other world that saw the other thing.
Make the other prediction.
Yes. So, strictly speaking, what I now have shown, so you can turn this whole thing kind of into a theorem, if you like, into a no-go theorem like Bell's theorem or so. And the theorem would say the following, namely, and this is, I will just summarize it here. I mean, of course, this can be made precise. If I make 3 assumptions, these are contradictory. So the following, so the theorem says there's a contradiction between the following assumption. The first assumption is quantum theory is universally valid. Validity. In the sense that it can, I mean, universal at least up to systems of the size that contain agents of quantum theory. The assumption C says that I can, okay, I think this is hard to describe on this small spot, but I call it just the consistency of reasoning about other people's reasoning. But it really just means if I'm certain that Matthias is certain about something, then I can also be certain about that, provided that I know Matthias is using the exact same theory that I would use. Of course, otherwise it would not be surprising, but I know Matthias uses exactly the theory that I would use if I was in his position. So I could even say that this means that if I take mentally the position of someone else and did the analysis there, and would come to a conclusion, I can take this conclusion also to be valid for me. Which is something we do, for example, in relativity. We talk about what if I was moving on that rocket, I would see that thing, and therefore this thing actually happens. And this is kind of a weak form of that. I just say if someone else is certain, then I'm also certain about that. But it's an assumption. And the last one is single outcomes in the sense of if I'm certain that the outcome will be plus 1/2, then I can be certain it's not minus 1/2. Which sounds pretty obvious, but it's violated in certain it's not violated in all many worlds interpretations, because in most many worlds interpretations you would still say you can make predictions with certainty that are true in that branch. But if you take a no histories approach where you jump between branches all the time, then this is not valid. But then you can anyway not make any predictions, it seems to me. So this is in that sense a rather weak assumption. Okay, but this concludes now the thing. So just to summarize, so you asked that at the beginning. So indeed, the standard Wigner's friend experiment doesn't really point to a contradiction of that type, because it's just different agents assign different states to systems. And if I interpret states as something that is just personal to agents, just reflecting their knowledge, then there's of course no contradiction because they have different knowledge. They have access to different information. Here, the point is that we make still an assumption which is, so, I mean, in all these analyses, one always assumes that. That's just the theory we have. We have no other model. So that's, I think, something that could be wrong, but we don't have an alternative. Here I added this assumption which is quite unusual in some sense, in the sense that it's not usually made explicit, but it's usual in the sense that we all the time use it when we interact. I mean, of course, if I interact with someone, I assume certain consistency in that sense. So I assume, for example, that if someone is not lying and he is convinced of something, then and use the same theory, then I could also. I mean, this is essentially learning. Otherwise, I couldn't learn from anyone else. I would have to see everything myself. Because if someone tells me this was like that, and I take this for certain, then I've already used this consistency assumption. So it would make it very hard to live in this world if this wouldn't work. Maybe we can replace it by a weaker version, but if we would give that up without replacement, it would be a very solipsistic thing. But okay, maybe there's a weaker version of that. And this is the third thing. So we have seen that if we take these three, there is an actual contradiction. Now, of course, the whole point is one of these three must be wrong. I mean, I'm not claiming here, so in some way I try to convince you these are weak assumptions, but at the end the point of the talk is one of them must be wrong. I don't have no clue which one. 2 years ago I was kind of thinking about that, but in the meantime, after many discussions which this caused, I essentially retract from any opinion, and I'm just essentially have no clue where to go from here. I just see there are three reasonable assumptions that individually sound to me all unproblematic, but apparently their combination leads to a contradiction.
So okay, what experiment would you do?
Yes, so what experiment? So that's of course we cannot really carry out these experiments, but of course we could. So the only assumption we could confirm by experiment is of course that one, because that's the assumption. I mean, we could really try to do. I mean, if we could do a measurement on an agent, really, whatever that means. I mean, one possibility is, for example, to simulate an agent with a computer and then say, this counts now as an agent. And then it's maybe feasible to do that measurement. So, I mean, that's one thing I could imagine. If one takes the assumption that a simulated agent, so if I simulate, let's say, Matthias on a computer, then it's still Matthias. And then I could do that experiment if I had a quantum computer, because a quantum computer would allow me to perfectly isolate the system and so on. So I think this assumption can be confirmed, whereas, of course, this I don't see directly. If I don't have consistency, then everything can always change, and so I.
Well, you catastrophize that by saying we can't learn if it's not true. But if you can't even do an experiment to test it, then
I mean, it's like
learn away.
Okay, I mean, we have the same situation as in Bell's theorem in that sense. So there's one assumption, which is that quantum theory is correct, which was tested. So all the Bell experiments test that assumption. And then there is a locality assumption and so on, which doesn't. So I see it really as a sort. So what it tells us, I don't think. So suppose we had an experiment which confirmed that. Then it's now the task of the theorists to find a theory which avoids the problem that comes from these. So the point is just we don't have any interpretation of quantum mechanics which is good here. So we don't even have a theory in some sense that avoids this problem. And so in that sense, it's a task for the theorists to find an explanation of this sort of experiment which avoids the problem. So in some sense, I see this contribution, just there is an experiment. It's like the black hole information paradox. There is a problem, and now this means there's something wrong in our understanding of the theory or in the theory itself. And this is the theorist's approach to do it. So we work with thought experiments and try to make sense of them. And the thought experiments can lead us to new theories. But we don't need the experiment except for maybe testing that. But maybe we could anyway now come to the question session. I'm essentially done with the main part of the talk. Yes?
So if we actually try to do an experiment, I guess we should try to understand deal with like knowledge robustness, like how these statements.
Yes.
Because somehow.
That's a very good point.
Statements
Yes.
are like, I'm certain. of
Yes.
something. In the real world, I'm never certain.
Yes. So indeed, that's a good point. So if we would, of course, carry them out, we would never be absolutely certain. Now, the good thing is that this experiment is kind of robust because, let's say, if I'm certain to 99% that you are certain to 99%, then this translates probably in some certainty about the thing you said, which is lower than 99, but still well above 50%. And now, of course, at the end, I end up with a statement which is of the type, W is certain up to, let's say, 95% that this happens. Now, that's good enough to, in principle, test, because if we have a physical prediction that tells us something is certain with 95%, but we never see it, for example, then at some point we would also say this theory is a bad theory. Although we can never be certain, we could always have been unlucky. But this is then just a statistical test of the theory. So these whole considerations are robust in that sense. I would just have to replace the final statement. I would replace the certainty by, I'm confident with probability 9%. Yes?
You put a lot of emphasis on the different times at which things
Yes.
happen. And in your analysis, I can't really see the importance of all
Yes.
these differences. It seems like it doesn't really matter.
Yes, you're right, it doesn't matter. And the reason I'm stressing that is as soon as you go into particular interpretations, it matters. So if you just take quantum mechanics so this Q is essentially free from interpretation. It's a minimal thing. It's just saying if the Born rule tells me that something has probability 1, I write down it's certain. That's the only interpretation I use. But now there are many interpretations like Bohmian mechanics. So, and in these interpretations, it actually matters when you do these things. So for example...
That's Bohmian interpretation. Bohmian mechanics is not an interpretation, no? It's a change of it.
Yes, it turns out in this experiment, it actually changes the predictions. So indeed, yes, that's actually what's happening. So in this experiment, what's going to happen is that the prediction we derived that this person makes, F bar. So we said if F bar sees that, then sees, for example, tails, then he's sure that W will see fail. This prediction is wrong in Bohmian mechanics. If you do the calculation in Bohmian mechanics, you just get the opposite. But if you now change the times, it will again be right, but then another one is wrong. So actually, which one is wrong in Bohmian mechanics depends on the timing. And the same is true for cubism. They would not agree with the prediction if the timing was, in certain senses, different.
Cubism also not an interpretation, but a change? Or?
No, but they would say that certain statements cannot be made. So for them, it's important that the predictions are always about future measurements. So one has to be careful that one is never talking about things that happened in the past. And so it sounds as if there's something in the past, but actually, for example, if this person talks about R that was seen here, then at the point where he makes the prediction, he could still test it in principle. And this is very important for the Bayesians. They always say that a thing has to be in principle testable. And so the choice of timing is done in such a way that always the thing you're talking about is in the present or in the future still available.
So what happens if we throw parts of this into a black hole?
Good question. I have no idea. I don't know enough about black hole physics, but maybe at the end of this workshop I will. But maybe I should make one remark. So you can now go through all interpretations, and you can kind of classify interpretations. So you can, for example, say, Bohmian mechanics now disagrees with Q, because it just gives different predictions. For example, Bayesian cubism disagrees with that. I mean, I had a long discussion. This is not obvious, but after discussing for days with Chris Fuchs and Rüdiger Schack, we came to the conclusion that it violates this. Many worlds is not so clear, actually. I always thought it violates this, but it's actually not clear, because depending on how you define branches, it shouldn't violate that. And then you can go, for example, consistent histories violates this. Because it's always about one history, so it doesn't, consistent history kind of makes explicit in some way you cannot have this type of consistency in some way. And there are many, you can go through any interpretation, you will always find at least one must be violated, of course. And so you can classify them in that sense. Yes?
I guess I was just going to say, maybe it tells me what interpretation I believe, but It seems obvious that consistency can't be done, because you're reasoning about people whose life doesn't matter because they were uncomputed again.
Yes, but okay, here
And
again the
I
time.
should reason about how those people reason about things and expect them
Yes.
to be right.
No, actually, this is again why the timing is important. So if you go through that again, you will see that I'm always reasoning about people who still are at that time have not been measured again.
Yeah, but they will be.
Yes, there will be, but of course you will. If you now make a
If they
prediction.
wrote down their reasoning and put it on a postcard to you, it would screw up the experiment. So
Yes.
they have to unexist after this, after having made this.
Yes, but you see, whenever, so for example, it would be like you make a prediction about something that happens in 100 years. And now I'm reasoning about the prediction you make now. So I'm now reasoning about you do now. And now I say I take this prediction to be my prediction about what happens in 100 years. So if you, me too, by the way, but if we now both die in the meantime and something happens with our brains where this prediction was stored, then
It's like reasoning what the guy who saw the photon go through one of the two slits would say, even though I know the photon didn't go through either of the two slits.
yes, no, but here you know, I mean, that's the point. You can always make this certain prediction. So that's why it's important that we only, I only combine things I already know. So I'm not saying you have seen the photo